So, our present objective is to go through chapters 15, 16, and 17, as you see the topics outlined here. Acids and base theories represents the first topic, and then we'll bridge that into the what we call weak acid or acid-base equilibrium, which revolves around what we call weak acids and weak bases, for those that would remember from early courses, if you've had this. And so we begin with the theories and talk about what an acid is and what a base is and some of the characteristics of it, and then we'll move into talking about the structural properties of acids and bases. So we begin with, if I can get my pen to work. When we talk about the concept of acids and bases, we are talking about the behavior of molecules in reaction environments. And specifically, it's aqueous media. And what that means is that when you add an acid or when you add a base into the aqueous media, two things have to happen. One, it has to be in water. As the solvent. I call it, you'll see me use this, water solvent in some cases. And ionization must occur. In some reactions, reactants, and you've seen this on the exam and practice, go to products, plus say HCl in the gas form. Well, in that form, in gas form, we do not classify HCl as an acid. We classify it as hydrogen chloride in the gas form. However, if this is outcome of this reaction is fed into water, it then becomes HCl in aqueous medium, which will ionize to the hydronium ions, aqueous, and chloride ions, aqueous. So these two issues must be present to call an acid or a base a base. And we'll talk about classification of those in a minute. When the reagent, acid or base, is in water, it functions as what we call electrolytes. Well, the term electrolytes comes from the fact that the reagent in water will conduct an electric charge, electro, as you might guess. In classifying the electrolytes in this study, we have three forms of electrolytes. Well, actually, one's not an electrolyte. Strong electrolytes, weak electrolytes, and non-electrolytes. Which you understand now, some of them don't ionize. But the central issue in an electrolyte is that it is a compound in water that undergoes that ionization and is required. Now, how much ionization is associated with the strong electrolytes? How much ionization is associated with weak electrolytes? How much is associated with non-electrolytes? Well, when we talk about those reagents that are strong electrolytes, we assume 100% ionization. And weak electrolytes is simply less than 100% ionization. And of course, the non-electrolytes would have components in the compound that would appear to be acidic in nature, but actually they do not do not undergo ionization, so therefore they're non-electrolytes, 0% ionization. Like that. So now we want to translate the idea of electrolytes into acid bases, and so we can call them strong or weak electrolytes, or, well, the only reason I put that term non-electrolyte in there is to emphasize that no ionization actually takes place in molecules. Well, you won't have any interest in those anyway, but I thought it would be a good point to say, okay, some things go in water fine, sucrose, sugar, those dissolve to white nicely, but they don't ionize, and they don't give a pH change and all that. At any rate, acids and bases in the electrolyte arena are referred to as strong acids or weak acids, strong bases and weak bases. So we want to tell you what the strong acids are and what the weak acids are. So in the following, strong acids called the strong mineral acids include HCl, HBr, HI, HNO3, HClO4, and H2SO4, first ionization step. The first row, and I'm noted here, are what we refer to as monoprotic acids. And that this hydrogen that is the formula that I'm showing you will, when placed into water, break away from the remainder of the molecule and be what we call the acidic hydrogen. Now, hydrogen does not float around by itself. Hydrogen as an ion, H plus, is a proton. Well, you don't find that. So we'll see in a few minutes or later on in another topic that this is actually an hydronium ion, which is H3O in its nature. H3O is a cation, like that. But for shortcut purposes, we just call, anytime a hydrogen comes off of a acid in ionization, it will become a hydronium ion, but we don't show it in that context, just for brevity of what we're trying to do. Now, next thing is H2SO4 to the first ionization step. Well, this is a diprotic, or in general polyprotic. There are H2s acids, and they're H3 acid, H4 acid, H5 acid in some cases. So what we're talking about here, this is a diprotic or polyprotic, and diprotic in this case, acid. And what that means is it ionizes in 2 steps. So when I say the first ionization step, that would refer to losing one of the hydrogens, not both of them at the same time. So the way that's written, say if we start with H2SO4 in aqueous medium, and we show that 100% ionized for just one of the hydrogens, we get this, which is anhydronium ion, plus HSO4 minus in aqueous medium. So that's the first ionization step. The second ionization step is this, the ionization of the bisulfate, HSO4. It is not a strong acid. It does not ionize 100% and is in itself a weak acid, which we'll talk about in a minute. So HSO4 minus in aqueous medium, and we can leave out the water because it's part of the process, but we'll talk about that in the theories, is in equilibrium. So I use that double arrow now with the more hydronium ion, aqueous, plus the sulfate 2 minus ion, as I'm showing you here. So this is the only one that's 100%, but this one, the bisulfate, does not ionize 100%. So if in a problem you're given HCl, HBr, HIHNO3, HClO4, you want to ionize those 100%. So one of the things I tell students to identify the ionizable hydrogen in this molecular notation is from left to right. Note the first hydrogen is the ionizable hydrogen, and everything after that is what we call either the anion component or the polyion, which will be negative component for that structure. So first is the first hydrogen is the ionizable hydrogen, then everything behind that one is an anion. And they can come quite different. We'll explain this when we get a little deeper into the course, but a weak acid, as an example, acetic acid, and has a HC2H3O2 formula, molecular formula, and you'll see that, and I'll show it to you in a few minutes, as an acid. Well, how does this undergo ionization? Well, I mentally draw a line between the first hydrogen out here and the rest of it, and in aqueous medium, it will break that hydrogen off into aqueous medium and leave a C2H3O2 minus in aqueous medium. Notice this one has some hydrogens in it also. These are non-acidic hydrogens. That means they are bound into the structure of the acetate structure so tightly that hydration doesn't occur, or they don't break away for right now. We'll talk about hydration later. But they don't break away. The only one that will break away is this one, and we'll talk about the reasons it does when we get into a deeper part of this section. Okay, so this is the introduction to some notations and terminology of acid and base, and why an acid is an acid. And we haven't talked about the basics yet, and why base is base. Okay. Strong bases. as electrolytes. Just like I listed the strong acids above, the 6 strong acids, I'm going to just give you what is considered the strong bases. These represent group, periodic table, group 1A and group 2A hydroxides. The base ion, of course, is the hydroxide ion, which is negatively charged. So just to reinforce this idea, here's group 1 and group 2 on the periodic chart. Group 1, when it enters into a reaction and combines with other elements, assumes a positive 1 charge. So everything in here has an outer valence electron of 1. Everything in this second column has a valence electron of 2. So in these 2 columns, their valence electrons are going to be lost. And then comes the anion that attaches to the metal. This is the alkali metals, alkali earth metals. And so hydroxide comes in and connects to the metal in appropriate ratios. For example, if we have sodium, for example, okay, plus 1 charge is in group 1, aqueous, or let's just say sodium, I'll just show you. Aqueous, sodium plus 1, chloride minus 1 will give you, give me a break. Hydroxide, sorry, will give you the sodium hydroxide, like that. Well, that's a 1-to-1 combination. And so when this ionizes, that is a group 1 strong base. And it ionizes how much? 100%. So if this is your compound on the reactant side, you might keep in mind that when in aqueous solution, it breaks up totally. You will not find any molecules of sodium hydroxide. So it goes to sodium ions, aqueous, hydrated, and hydroxide ions, minus, aqueous. And so this little notation is true for all of the group 1 elements in here, the alkali metals, as a 1-to-1, and gives you the lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium, cesium, francium hydroxide. And when placed in the water, they ionize 100% and deliver the alkali metal and the hydroxide ions. Now, group 2 is going to be plus 2 charges when they go into solution. Oh, I forgot to make one other note. Group 1A and group 2A hydroxides are your strong bases except for beryllium hydroxide. This is not a strong base. So you don't include that in the consideration of what's happening to that compound. It shows up in other cases we'll show you later, but this one is not in this collection of strong bases. In other words, it doesn't ionize 100%. Okay, so that was group 1 example right here. And a group 2 example would be something like, let's see, magnesium. Magnesium carries a plus 2 charge when in ionic state and will require 2 hydroxide to bind with the magnesium so that sum of charges equals 0. And so the molecular formula is magnesium hydroxide, subscript 2, put it in water, it's aqueous. I should have put an aqueous on that one too. And so 100% ionized is magnesium plus 2 aqueous plus 2 hydroxides aqueous. and I'm getting kind of crowded, but trying to prove a point. You will, in the strong electrolyte arena, you will only find ions. You will not find any molecular forms of group 1A or group 2A hydroxides. So all of the elements in group 2 are a +2 and therefore require 2 hydroxides. And so we'd have, except for beryllium, magnesium OH2, and then calcium OH2, stand by for me. Weak acids and weak bases. Well, of course we'll start with weak acids. Basically, ionize less than 100% in aqueous medium. However, the fact that they ionize and are in aqueous media classifies them as an acid. Now, the issue with weak acids, we can use a hypothetical in the following way. Say that's the ionizable hydrogen hooked onto an anion. Okay? And if placed into water, it will start ionizing and go to H plus anion negative. And we can see that as we've drawn concentration versus time. We have the H anion here, right here, and so its concentration begins to decrease like this along that trend, and the anion and hydrogen do ionize in equal amounts, so 1-to-1 ionization, except for those acids that are marked clearly as polyprotic. Anytime you see one hydrogen out there, it's a monoprotic, and it always ionizes 1-to-1. And whatever we do in the hydrogen is also applies to the anion. So I'm just going to show the hydrogen generated. So at the time the reaction starts, you have this trend that we've talked about in the past. And I just use HA for the acid concentration. And we recognize the differential between the kinetic and the equilibrium region. Now, what I want to say in here is what's happening in the kinetic region is that you have a steady increase of hydronium ions and anions. I might as well put that one in because it is a big player. And anions right here. Well, as the anion concentration increases to a point, it's such a strong negative charge, it starts re-attracting the hydrogen. Starts pulling back on these hydrogens. And so when that happens, what happens is at this point when it enters equilibrium, you have an equilibrium between HA and H plus A minus. And that's why it's a weak acid, because you will, at this point, you will have not just ions, but also molecules of the weak acid. This is a very important conceptual issue in understanding acid-base equilibrium when we get into that chapter. That the reason weak acids are weak acids is, yeah, they ionize, but at some point, shortly after they ionize, there's such a strong anionic charge, they start sucking back on the hydrogens and recreating the molecular form of that acid. And so that's a real critical, and you'll see it when we get there, how that is important in there. Well, all weak acids do the same thing. It's just some do it more than others. Okay, and that's when the K value comes in, and we call them acid ionization constant, which indicates what the extent of reaction is. You recall from the last chapter, some will give you a large extent of reaction before they start reversing, or some will give you a very small extent of reaction before it starts reversing. Okay? And these are called Ka values, which are indicators of when it enters the equilibrium region, and these are called acid ionization constants. In Ebbing's text, Table 16, 9th edition, but Chapter 16, all of them have the same table. You'll see, like, acetic acid, and I showed you this earlier, has the ionizable hydrogen here, but these are non-ionic hydrogen, and we'll show you that later. And it has a K value over here. So it's 1.7 times 10 to the minus 5. You can't see it from the cheap seat. But anyway, benzoic acid, straighten the book up so you don't get vertigo. Benzoic acid, C7H5O2, has a Ka value of 6.3 times 10 to the minus 5. Since benzoic acid has a bigger value, 6.3 is larger than 1.7, that means benzoic acid is a stronger acid. That refers to it sending more hydronium ions into solution than is the acetic acid. So that's what the idea of weak acids is in terms of the analytical numbers that describe those reactions. And you can see all of these have a hydrogen out front. Some of them have them buried in the anionic structure. And they all have different K values. And we have an experiment that you will do, and I'll show it virtually, how to calculate the Ka value of, say, acetic acid, and how we get this number when we do an acid-base titration. At any rate, it ionizes but doesn't proceed very far before it reverses and generates the molecular form of the acid, weak acid. But strong acids, you will not find any molecular forms, and the all ions that are generated in solution. Okay, weak bases are defined or classified as are ammonia, or ammonia derivatives and one of the hydrogens is taken off and, say, some substituent group is placed on the ammonia molecule, and so you have a substitute for one of the hydrogens. It's called ammonia derivatives or amines in water. Now, here's a notation that you want to get kind of in your head as far as formatting. On test day, the weak base, say if it asks you which of the following is a weak base, and it give you a list of compounds, the weak base, say if it asks you which of the following is a weak base, and it give you a list of compounds, the weak base, say if it asks you which of the following is a weak base, and it give you a list of compounds, the weak base, say if it asks you which of the following is a weak base, and it give you a list of compounds, the weak base, say if it asks you which of the following is a weak base, and it give you a list of compounds, the weak base, say if it asks you which of the following is a weak base, and it give you a list of compounds, the weak base, say if it asks you which of the following is a weak base, and it give you a list of compounds, the weak base, say if it asks you which of the following is a weak base, and it give you a list of compounds, the weak base, say if it asks you which of the following is a weak base, and it give you a list of compounds, the weak base, say if it asks you which of the following is a weak base, and it give you a list of compounds, the weak base, say if it asks you molecular form, comma, not the hydroxide will be shown. This is a formatting and a common practice in the chemical community when working with these. For example, if you have a weak base NH3, that's the way it will be posted in the exam. However, that's not the chemistry of the weak base. The chemistry of the weak base is when NH3, the ammonia, which has a non-bonding pair associated with the central element, is placed into water. Well, I'm going to write it out this way. What happens is this has in water is a polar molecule which is positive on the hydrogen end of this notation, and negative, of course, is the hydroxide ion. And we write in there, say, a little S with a tail on it, and put a positive on it, and that's what is positive end of the molecule, and put another little S with a negative, and that represents the negative end of that molecule. Well, that is attracted to the same issue over here because the electron pair polarizes that molecule and makes it negative in nature also. And so this hydrogen, we'll call it the acidic hydrogen, will coordinate with the electron pair called coordinate covalent bond. And we'll get the following, I'll put it this way, HO, and then H, and then the electron pair will be responsible for forming the bond like that. And this is typically noted, this is absorbed, it should be a 3, sorry. This is typically noted in the following format, NH4OH. Now that's the ionizable weak base, the hydroxide of the ammonia. And the only difference between this and the ammonia derivative is one of the hydrogens has been removed and you put a substituent R group on there, whatever it is. But it's still a derivative. Now, to see that in a more direct format, what you have is say NH3 plus H2O, and this could be any of the derivatives also, will always one way, 100% conversion, and water in the ammonia will go to NH4OH, which is the base. And when you identify this one, it is, of course, breaking the OH off. That's your ionizable hydroxide, and it becomes a weak equilibrium NH4 between NH4 and the hydroxide, and it functions just like the weak acid did. It begins to ionize, delivering ammonium ions and hydroxide ions in solution, but as the ammonium ions increase, it reaches a point at which the reaction reverses itself and it enters the equilibrium region. Because of the strength of the cation, it starts pulling back and bonding again with the OH by electrostatic attraction. So that's the essence in chemistry of weak acids and weak bases, strong acids and strong bases. Remember that in the weak electrolytes you have 3 forms in solution: the molecular ionic cation and anionic anion, negative anion. At any rate, in the strong acids, remember there are only 6. So how do you identify all of that something is a weak acid? Simple. If it's not a member of that strong 6, it ain't strong acid. So whatever it is, whether you know what it is or not, it's going to be a weak acid. You don't have to know that list of weak acids. You just have to know the list of strong acids. HCl, HBr, HI, HNO3, HClO4, and H2SO4, first ionization step. And so if we write out something that doesn't match that, HC2H3O2, and tell you that's an acid, it's strong or weak, you don't have to know what it is. It is a weak acid because not member of strong 6. HCl, HBr, HI, HNO3, HClO4, and of course H2SO4, first ionization step. Is the general character of acids and bases. Some of you have heard of these before, like an acid sour, base is bitter, and all that, and there's some others. Well, I made up an acronym many years ago that helps the student kind of keep these in mind, and it's GRIT. Acids and bases, G stands for galvanic. That is, they conduct electric charge. So if you built an electrolytic cell, and we're not going to go into that, and hook batteries to it, you would have a flow of charge, and it would be as a result of the ions of the acid or base, whatever you're using, moving between the electrodes. And we'll get to that when we get to electrochemistry. This is react. That is react to yield a salt and weak electrolyte. And that weak electrolyte in this is a driving force of a metathesis reaction. If you've had me from last semester, you'll certainly remember how to define what a driving force is. It's that reagent on the product side that leaves the system and pulls the reaction to completion. HCl plus NaOH goes to NaCl, salt, plus H2O. Well, this is the driving force because it's now not in the form of these other compounds. These are in ionic form. That is, they split and become ions in solution. But water, the driving force, is in molecular form, different from the ionic form, and that's essentially why it's called a driving force, and of course it leaves the system and the reactive nature, but it's always acid plus base, it's a salt plus a driving force. Now I can show you reactions, and we'll get into this when we get into theories next time. Acid plus base gives salt, but not necessarily the water as a driving force. So there are, and that's what that little list of compounds on the handout I gave you is all about, and we'll talk about that next time. Indicator sensitive. Okay, indicators, I'll move that up here. Indicators can be like the BTB you use. When you put it in an acid solution, it's yellow, and the base solution is blue. But there are other indicators, and one that I want you to know about is litmus paper. And it comes in two forms, red litmus and blue litmus. These are just little 1-inch strips, about a 1/4 inch wide maybe, and you take a sample of it and you put the end of that strip into a liquid you think is an acid or base. If it changes color, then you're able to identify it as an acid solution or a base solution. Well, and you have two strips, one red, one blue. You use both of them, see which one changes. Red goes to blue in a base. Remember the B in base. Red turns, the litmus paper is going to turn to the opposite color. Okay, that's a given. Now, if you're using red, it changes color. It's a base solution. If you have blue litmus and you test the solution, it turns red in acid solution. So red litmus goes to blue in base, B base. Red turns to blue in acid. So you memorize it any way you want to. Okay, the last term up here, the last letter in here is everybody's favorite, taste. And there are only two tastes that will characterize acids and bases: sour and bitter. The bitter, of course, is the base, and sour, like a lemon, is the acid. Probably already knew that anyway. But if you didn't, look at the B's: bitter, base, and then the other one, sour and acid. Only two.